Hello, everyone. We're gonna get started. So Monday we covered simple regression model, and today we're going to cover multiple regression with the multiple independent variables. I think it's somewhere in the waiting room. So let me share my PowerPoint slide. Now we're going to cover multiple regression analysis today. So Monday we covered the simple regression model with only one independent variables. If we have multiple continuous independent variables, I'm just saying continuous independent variables because we didn't deal with binary variables yet. So multiple regression analysis is very common. So most regression problems involve more than one independent variables, usually at least 2 or 3 variables. Sometimes you have a 5 to 10 variables, but if you read some research articles, they may have 15 or 20 different independent variables. If you have many independent variables, you need to have a large sample size. But in this textbook, we only have 10 or 12 observations, which is sample size equal to 12. So keep that in your mind. If you need more independent variables, you need to have larger sample size. So for each independent variables varies in a linear manner because we're dealing with linear equation with dependent variable y. If you see actual regression model would be y with intercept, this is intercept. But we're going to use alpha for the coefficient of independent variable, we're going to use a beta. So first, independent variable, this is a continuous variable. Second, independent variable with beta 2. Then we're going to have k number of independent variable with error terms, because this is actual regression line, which is function. So each observation will use this equation to estimate, to get the response variable y for ith observation. So that means first observation will have beta 1 x11 plus beta 2 x21 beta k xk1 plus I. So you're going to have n number of these actual regression function, but because we cannot have all observation in the population, we just need to have a sample using smaller sample, which is a part of a population. So we're going to have estimated regression line, which is a regression function. So we're going to estimate y response variable with intercept A0. Instead of using alpha and beta from population, we're going to use A and B for estimated regression line. So it's going to be B1x1 plus B2x2 for BK x k number of observation. This k is based on the size of the number of independent variables. K number of independent variables. Now we don't have error terms because this is estimated. If you estimate y response value of y using this equation, that's a first observation. So we're going to have let's say ith observation. So as you see here, these x on the x-axis, on the vertical format, we have y. So I have intercept A0, while you have slope B is so now different things from Monday's class. We have k number of independent variables. We only consider continuous independent variables at this moment, but we're going to go with the binary independent variables. So the optimal values for the BI can again be found by minimizing the error sum of squares. The resulting function fits a hyperplane to our sample data. So with a simple regression model, we use a 2D plane. But if you have multiple independent variables, we're going to have hyperplane. So it's difficult to visualize. So here's an example from the textbook. A real estate appraiser wants to develop a model to help predict the fair market values of residential properties. Once you buy your house, the county or city will send appraiser to your house to make sure the price can be used for tax collection. So there is a process from real estate or city administration. So in this case, so we're going to have an example with 3 independent variables, right? Such as total square footage, number of bedrooms, and size of the garage. So we have 3 independent variables. So you may say x1 and x2, x3 for them. And then y will be selling price of a house. So we have a response variable, which is selling price. And then we have 3 independent variables in this example. So k equals 3, and we'll see how many observations we're going to have.
What happened upstairs again?
So first thing is we want to identify the simplest model. So if you have 20, 30 variables, that'll explain your business better, but some of them are necessarily redundant and it make the model complicated, so it's very difficult to understand and it's tough to use that function to predict the response variable of y. So the model should be simple enough and that model should be accurate to predict. That means we're going to minimize systematic variation and unsystematic variations in the y variable. So if you have many independent variables, the model will be overfitted. That means you may have many redundant variables, so it takes time to run the model and it's very difficult to calculate. And sometimes it gives you a bias because it is overfitted. And so you need to be very careful with that. We always need to understand the characteristics of the sample because sample represent the population. We want to have a very good sample, which is randomly collected. Right? So as I told you, we want to avoid any fitting sample specific characteristics, which is overfitted. So that give you very high R-scale values, which is goodness of fitness test, but that's gonna be overfitted. So again, we should be very careful with that. So again, keep this in your mind. The model should be simple enough to represent the population. So that means we need to have an accurate model. So let's go with the sample from the textbook. We have three not decision variables, independent variables. And then we have 11 observations. So what our simple linear regression model? So if you just run the regression analysis with the first decision variable, no, not decision, independent variable, then your predicted value of y will be a0 plus b1 x1 for the ith observation. You may find I used A0 instead of using B0. Textbook uses B0, so it doesn't matter because it's an intercept. And if you don't like A0, you can use B0. So for this is the first independent variable. For the second independent variable, we can use second independent variable to predict response value of y. We're going to use the same intercept, not same. So the intercept value will be different, but we have the same label. And this coefficient will be looks same, but it's not actually same. Because depend on variables, the model will give you different intercept and slope. And the third independent variable, we also give you response values in the third variable. Then if we go with these simple linear regression model, we're going to have R-squared values for with first variable and second variable with third variable. So you will get these values. We're going to use Excel to demonstrate. And we also are going to talk about adjusted squared value for third variables. So as we had a discussion, and R squared value would be R S S over T S S. This is equal to 1 minus ESS over TSS. Will be the same. So if R squared value approaches to 1, that means we have a good fit. If it approaches to 0, it doesn't fit the data. So using each regression, simple regression model, we're going to estimate A0 and B1 for each regression. Then you may try to pick the best fit model based on R-squared value or adjusted R-squared value. So if you run this with the sample data from the textbook, and you will get the highest R-score with X1 decision variables, X1. X1's R-squared value would be 0.87. That means the model using independent variable X1 accounts for 87% of variation in Y response value, leaving 13% accounted for. So just one thing you need to be careful with Excel regression analysis is you need to have X values which are contiguous. If you have separate columns for independent variables, then Excel cannot recognize them. Now suppose we fit the multiple linear regression model with the 2 independent variables. So because we have 3 independent variables, we have 1, 2, 3 combinations. We have 3 independent variables, x1, x2, x3. So we can predict y with first 2 independent variables. So we use 2 independent variables of x1 and x2. Then second model is to predict y with first and third, let's say, okay. If you read the textbook, it says B3, but I'd say B2 because we have a 2 coefficient. But to avoid any confusion, I can say that this is B3. But actually, we have only 2 coefficients. Just keep that in your mind. We have third model with second and third independent variable. So 1, 2, 1, 3, and 2, 3. We have 3 different multiple regression lines with the 2 independent variables. Now you're going to run each regression model, right? And then from the previous simple regression model, we learned this simple regression model was the best with R-square value with 0.870. Now we're comparing this single regression model with 2 multiple regression models. We're going to use R-squared value to see which model fit the data best. So we're going to run each one, but in the textbook, we only ran with 1, 2, and with 1, 3. So we compare the single regression model and multiple regression model. So if you run the first one, the R-square value as 0.939. The second multiple regression model is 0.93. Oh, no. Yeah. 9.3. Yeah, that's correct. No, that's 8.77. So now see which function has the highest R-square value. So this one, right? Now this multiple regression line is the best so far. Thing is, if you add any variables, independent variables to the model, you're going to have more independent variables, then that increase your R-squared values. However, between these two, these models have the same number of independent variables. So the first one has the highest R-squared value. So this model using X1 and X2 accounts for 93.9% of the variation in response values of Y. So as I said, as additional independent variables are added to a model from single regression model to multiple regression model, the R-squared statistics can only increase So that means if you add 10 independent variables, 20 independent variables, your R-square value will be increased. However, that actually distorts our analysis. So we're going to use adjusted R-square statistic instead of using R-square statistic. Because adjusted R-square statistic use freedom of sample size. So in other words, R-square statistic can be artificially inflated by adding any independent variables. In this case, we have 2, but you have 3 and 4. The R-square statistic will be increased. So now let's see if you add independent variable x3 onto this multiple regression model. So our prediction model will be a0 plus b1 x1 I plus b2 x2I plus b3 x3I. Now we use 3 independent variables. And we also test. We can test this model y I a0 plus b1 x1 I plus b3 x3I. So now we see x1 and x3 because our decision variables, no, not decision variables, independent variables, x1 represent square feet, x1 square feet, x2 is size of a garage, x3 will be number of bedrooms. Okay, now if you have square feet and number of bedrooms, then there'll be 3, then R-square value there 0.877. Now we see, even if you add another independent variable onto this simple regression function with R-square value 0.8707, the R-square value for new multiple regression model just increase a little bit higher than simple regression model. The reason is x1 and x2, x3 variables are very similar. That means number of bedrooms is highly correlated with the square feet of the house. So one of these two variables, no, these two variables, maybe one of these two variables are redundant to use. Because as I said, if you have many variables, you need to increase sample size, and it's also more complicated to translate into business world. So we knew x1 independent variables explain the housing price very well. Then other variables, so we can use x1. We're not going to use x3, so we can go with this model x1 and x2, right? Or x2 and x3, but x1 is better than other variables. So we're going to choose x1 and x2. Now we need to compare these two independent regression model with three independent variable regression model. So if you have three of them, and the R-square value is 0.943. Nine four three, right? Now you see, let's say this is the first model, and this is second, this is third, and now simple regression model, two independent multiple regression model, three independent variable multiple regression model. So now see, if you add extra independent variable, your R-square will be higher. But that doesn't mean this model is the best, because that has distortion. We're going to have adjusted R-squares. So with single independent variable, adjusted R-square value is 0.855. With the two decision variables of x1 and x2, adjusted R-square is 0.924, while three independent variable model give you 0.914. See, even R-square value or value with the three independent variable is higher than the other model. Adjust R-square value with two independent variable will give you the best fit, the data. So instead of using all three independent variables, we may use x1 and x2 to predict the price of a house. Okay, so any questions so far?
Nah, we're good, Professor. Thank you.
All right, thank you. And the chat box. Chat box. Okay, so let me read the chat box. All right, the optimal values for the coefficient B1, B2, Bn can found by minimizing the sum of scale. Yes. Yeah, so that is a ESS. Or the sum of squared residuals, RSS, between the observed values of Y and the predicted case. So we're trying to find the coefficient of B1, B2, which minimize ESS. While maximizing RSS. Okay, so that's what I explained. Okay, so using these multiple regression, if we want to estimate average selling price for the case of 2001 square feet with a 2-car garage. This is X1 and this is X2. So you want to predict Y, right? Using, so we have intercept 127.64 plus B1 coefficient of X1 as 38.576. X1 is 2100 square feet plus B2 is 12.875. And then X2 is 2-car garage. So average selling price for this house is $234,000. This is estimated average selling price, because this is not concrete value, but it's going to be fluctuated between lower level and upper level. So this is estimated average selling price. Okay, so if you say this is average selling price, right? For this case, right? It might be lower, it might be higher than that. So as you remember, based on different X level, you have different value of Y. This is actually normally distributed with average value of Y, right? So we try to connect these Y values like that. So this is average price, right? If you want to consider the prediction interval, you may think of plus minus 1 sigma or plus minus 2 sigma plus minus 3 sigma. So if you have plus minus 1 sigma, that explains 65% of the variation. If you used plus minus 2 sigma, that explains 95% of the variations. So if you use plus minus 3 sigma, that explains 99.9% of the variations. So we're going to use 95% prediction interval. So you can get the equation from the textbook, which is we estimate Y interval value using 2 standard error. Because we use sample, we use standard error instead of using population parameter sigma. So we're gonna go in depth, but you can get the equation to prediction interval of the housing price. So let me demonstrate the model using Excel. Get my mouse and mouse pad. Okay, this data is from the textbook. We have 11 observations. That means we have n equal to 11. Then we have 3 independent variables, x1, which is a square feet, and the unit of 1,000. And x2 is the size of a garage. x3 is the number of bedrooms. And then we have a housing price. So in this case, the unit of housing price is 1,000. So if you see 165, that means $165,000 for first house, and the second house is 173, and the third house 185. So definitely we understand price is the response variable we want to predict, and the other 3 variables are independent variables which affect the housing price. Now, if you have data, we need to see the pattern of the data. So we're going to draw a scatter plot with y response variable with each independent variable. So to draw scatter plot, we're going to draw, it's insert, on the insert, and you see chart icon. Then if you select the scatter plot, but we need to select the data first. Okay, let me select x1 and y1. The scatter plot. This scatter plot for square feet and housing. For the second, let's have x-axis. So this is I'll say x1 is y is. Okay, so we're going to draw the second scatter plot with the size of a garage and price. So select the range of x2 and y. Also go to insert and select scatter plot. We also see there is a linear pattern. Then x-axis. This will be x2. And this y, which is price. Let's draw a scatter plot with number of bedrooms and housing price. So we're going to add axis titles. So x3. And this is housing price. You see, there's a linear relationship between y, and x variables. So we're going to use these scalar plots to under the tab of now worksheet scalar plot. So we can make it larger. So now you see the linear pattern. Or if you wanna draw a regression linear equation on the graph, you choose the point and then right click on any point, then select add trend line. So you see the linear equations. I may do it again. Format trend line. See on the right hand side. See. If you scroll down over the format trend line panel on the bottom, actually on the top, you may select a linear, exponential, polynomial. Well, I think looks like a linear, so we choose linear. Then display equation on chart with R squared value. Now the R squared value is 0.79 with x1, and with this second one, we have equation and R squared value on chart. That is 0.86. And the third one, trend line. I'm going to choose a linear with equation and R squared value on the chart. Now close the format trend line pane. Now you see with x1 in the middle, R squared value is 0.86. With x2, R squared value is 0.75. With x3, R squared value is 0.79. So now we know with x1 will have the best fit model. In this case, you can make it larger. So that's the easiest way to draw trend line or regression line with equation, linear regression equation, and R squared values. Right. So you may use different way. Go to data. We go to data. And select, oh my gosh, no, the zoom manual bother me. Okay, so I'm going to make it small. Okay, under the tab data, you may find data analysis icon. If you don't find it, go to file, and options. Then you will find add-ins. On the bottom of add-in pop-up window, you can find X add-ins with the button Go. Click it. Then you need to check Analysis Toolpack on the add-ins pop-up window. Then click OK. Now you will see Data Analysis icon on the tab of Data Analysis. Then if you scroll down, you will find the regression. And then click OK. And input range will be the price. I'm going to select the range, including label. And then X range will be only X1. Then I highlighted the range, including labels. So I'm gonna check labels. I also want to have a 95% confidence interval, estimated prediction interval. Then I will draw residual plot to see the pattern of errors and normal probability plot as well. Then I want to have this output under the tab worksheet X1. So that's going to be X1 over here. Now click OK. So if you select worksheet X1, now you see the regression report with the normal probability plot and X1 residual plot. So the errors, the residuals is over under zero, normally distributed. So you also see normal probability plot as linear. So now we can pick the coefficient of intercept and coefficient of X1 from the cell C18 and C9 respectively, right? So that gives us regression equation. So now we know this is A0, this is B1. So let's see R squared value, which is 0.86. 0.86. If you see the scatter plot 0.86, you also have the same R squared value from this linear trend line. See, slope was 56, while intercept 109 with X1. So now you have the same number, right? Intercept is 109. The slope of X1 is 56.39. So you will have the same values. And you also have here RSS, regressions, sum of squares. The residual is ESS, error sum of squares, and then TSS, total sum of squares. And you also have two other values in column E. Are MS, it's a MSR on textbook, mean squared value of regression, right? MSE, mean squared value of error. So you also have F value, which is ESS over MSS, and significance F. Now let's go back to data one. Now we're going to generate regression report with X2. Again, we're going to click data analysis, regression. Now we're going to select X2 range. Then we're going to have output into worksheet X2. Then generate the report. Now we have intercept, slope of independent variable X2. Then we have R-squared 0.75. So we're gonna do the same thing with third independent variable. data analysis, regression, and then we're going to select X3. Then output range will be worksheet 3. Once you're done, click OK. So now we have new intercept and slope of independent variable x3. So go back to the data set. Now we're going to use two independent variables, x1 and x2, to generate regression analysis report. Click data analysis, regression. Now X range will be x1 and x2. Our output will be in worksheet x1 and x2. So now click OK. So now we have new intercept and then two coefficient for independent variable x1 and then x2. We have a new R-square value which is higher than simple regression model. So we're going to do the same thing with independent variables x1 and x3 with the data set 1. Data analysis, we do the same thing and then select X range, x1 and x3. So let's try to this way to see if it works or not. Then go to tab here and click OK. Now see regression input range must be a contiguous reference, okay? So it doesn't work. Now I'm going to move x3, cut, and then paste between 1 and 2. So now 1 and 3 are contiguous. So click data regression. Now I'm going to reselect x1 and x3. And then output range will be worksheet x1 and x3. Okay, click OK. Now we have new intercept and coefficients for x1 and x3 with R-squared value, which is lower than 0.90, right? So it's time to go back to data 1, having all 3 independent variables. So click data analysis, regression, and we're going to select x1, 3, 2, because we switch the position of x2, x3. It doesn't matter, we're going to run. And then we're going to have this output into a new worksheet named x1 and x2 and x3. Then click OK. Now you see R-square value with the 3 independent variables will be 0.94, right? But adjusted R-square is only 0.17, which is lower than this multiple regression with 2 independent variables of x1 and x2. So x1 and x2, 3 intercept and coefficients available. So now we know the model with 2 independent variables of x1 and x2 will be the best fit the data to explain the estimated price of y. So as you mentioned, there is a multicollinearity issues between x1, x3, because the variables x1, x3 give us very similar information because the number of bedrooms is depending on square feet. That means if you increase square feet, then you have a better chance to have more bedrooms. So what you can do is we don't know Excel doesn't provide any function to see the multicollinearity, but we can use a simple way to check correlation between between two independent variables. What you can do is go to data and click data analysis. Then you will find correlation and click OK. And input range will be 3 different independent variables. And then output range have you tab here, then click OK. Oops. What did it say? Okay, so that should be. Okay, let's try again. 13 output range. Let's just do it over here. And okay, now we see X1, X3 are strongly correlated, while X1 and X2 shows correlation of 0.74. If it is very close to 1, that means they have a strong correlation. If it approaches to 0, there's no correlation. So to use multiple variables, those multiple variables shouldn't have strong correlation. Now, I'm going to use the data set 2. We have 11 observations with the square feet, only one variable square feet. Let's draw diagram, no, scatter plot of this and draw, no, insert scatter plot. Thing is, chart style, no, add X titles, axis titles with a square feet, and here's the housing price. Okay, instead of going far, I can just use trend line here. All right, right click on the dot. You may select add trend line. Now, see, instead of using linear, because linear doesn't explain much, right? So if you click power or polynomial, right? And then second order polynomial, or you can encourage a third order polynomial. Let's go with the second order polynomial and have equation on chart and R-square values. Now we see R-square is 0.97 with this equation. Now, if you go with the third order polynomial, keep the number in your mind, 0.97. Now, third order polynomial give you higher R-squared values. You see this, right? 0.992. But if I go with second order polynomial, it has a lower R-squared values. So what you can do with this data set for the second order polynomial, you can make a square values of this squared and I copy this formula. Now, Actually, you have one independent variable, but we are making second independent variable. Those two are different independent variable for now. Do you understand?
Yeah, Professor.
Okay, thank you. So what you can do is go to data again and data analysis with the regression feature. Select price as Y, and for X range, now you're going to select X1 and X2 we just created. So we're going to put this maybe somewhere here just for test and click OK. Now you have regression statistic. So now you understand how works with polynomial regression.